Download this code from codegive.com, link in the description below. Apple Instruments Time Profiler, a deep dive for performance debugging. Apple's Instruments is a powerful performance analysis tool that allows you to pinpoint bottlenecks, memory leaks, and other performance issues in your applications. Among Instruments' many templates, the Time Profiler is arguably one of the most valuable for identifying CPU-bound performance problems. This tutorial will provide a comprehensive guide to using the Time Profiler, complete with code examples, practical scenarios, and advanced techniques. What is the Time Profiler and why use it? The Time Profiler is an Instruments tool that samples the call stacks of your application's threads at regular intervals. By collecting these samples, it builds a statistical view of where your application is spending its time. This information is crucial for identifying CPU-bound performance bottlenecks. If a particular function or code path appears frequently in the sampled call stacks, it indicates that your application spends a significant amount of time executing that code. Optimizing algorithms and data structures. Understanding where your application spends its time allows you to focus your optimization efforts on the areas that will have the greatest impact. Understanding threading issues. The Time Profiler can reveal if threads are spending excessive time waiting, being blocked, or are underutilized. Measuring the impact of code changes. Before and after profiling allows you to objectively assess whether your optimization efforts are actually improving performance. 2. Setting up a basic project for profiling. Let's create a simple Xcode project to demonstrate the Time Profiler. This project will perform a CPU-intensive operation, calculating prime numbers, that we can then analyze using Instruments. 1. Create a new Xcode project. Open Xcode. Choose Create a new Xcode project. Select iOS, or Mac OS if that's your target, and choose App. Give the project a name, example Time Profiler Demo, and select Swift as the language. Choose a location to save the project. 2. Add a CPU-intensive function. Replace the content of content-view.swift with the following code. 3. Build and run the app. Run the app on a real device or in the simulator. The Calculate button will trigger the CPU-intensive Calculate Primes function. 3. Launching Instruments and selecting the Time Profiler. 1. Run your app from Xcode. Make sure your app is running on a device or in the simulator. 2. Launch Instruments. In Xcode, select Product-Profile. This will launch Instruments and attach it to your running app. Alternatively, you can launch Instruments independently, open Spotlight, CMD plus space, and search for Instruments. Then, select your running app from the process list in Instruments. 3. Choose the Time Profiler template. In the Instruments template chooser, select the Time Profiler template. You might need to scroll down to find it. Click Choose. 4. Using the Time Profiler, a practical example. 1. Start recording. Click the Record button, the red circle in the Instruments window, to start recording data. 2. Trigger the CPU-intensive operation. In your app, tap the Calculate button. Observe the progress bar. 3. Stop recording. Once the calculation is complete, the progress bar disappears. Click the Stop button, the gray square, in Instruments. Analyzing the Time Profiler data. Instruments will now display a detailed view of your application's CPU usage over time. The Time Profiler instrument shows several key pieces of information. Timeline pane. The top section displays a timeline of CPU activity. Spikes in CPU usage indicate periods when your application was performing intensive tasks. Select a region of interest to zoom in on that specific time range. Asterisk call tree pane, call stack view. This is the most important pane. It displays a hierarchical view of the call stacks that were sampled during the recording. By default, it will show the heavy top-level function, where your application spent most of its time during the recording. You can configure how it's displayed and sorted using options in the detail area, the bottom section. Asterisk detail pane asterisk located at the bottom. This pane provides further options to inspect the data. Interpreting the call tree asterisk. The call tree pane presents a breakdown of CPU time by function and call stack. Understanding how to interpret this data is crucial for identifying performance bottlenecks. Here's a breakdown of the common columns. Asterisk symbol name asterisk the name of the function, method, or block of code. Asterisk self asterisk the percentage of time spent directly executing code within that symbol. This is the most important metric to focus on initially. Asterisk total asterisk the percentage of time spent executing code within that symbol and all of its calls, functions it calls. This shows the overall impact of a function and its dependencies. Asterisk samples asterisk the number of times the call stack was sampled when the application was executing within that symbol. Finding the bottleneck asterisk. 1. Focus on self values asterisk sort the call tree by the self column in descending order. The functions with the highest self values are the most likely bottlenecks. In our example, you should see is prime, underscore and calculate primes, count near the top. 2. Examine the call stack asterisk expand the call stacks of the top functions to see where they are being called from. This helps understand the context in which the function is being used. Look for patterns that might indicate inefficient usage. 3. Identify redundant calls asterisk look for functions that are being called repeatedly with the same arguments. Consider caching the results of these calls to avoid redundant computation. 4. Look for expensive operations asterisk identify operations that are inherently slow, such as I/O operations, complex calculations, or large memory allocations. 6. Advanced techniques and considerations. Asterisk filtering and grouping asterisk. Asterisk filter by process asterisk if you're profiling an app that uses multiple processes, you can filter the time profiler data to focus on a specific process using the process drop-down in the detail area. Asterisk filter by thread asterisk similarly, you can filter by a specific thread using the thread dropdown. This is useful for debugging multi-threaded applications. Asterisk invert call tree asterisk in the details pane, under call tree settings, you can check separate by state and invert call tree. This allows you to see the call tree starting from the application delegate and drill down to find performance-intensive areas. Asterisk addressing framework overhead asterisk sometimes, you'll see significant time spent in Apple frameworks, example UIKit, Foundation. While you can't directly optimize the framework code, you can optimize your use of the framework are you using the framework APIs in the most efficient way? Are you doing unnecessary work that the framework already handles? Defer work to background threads if the framework calls are blocking the main thread, move the work to a background thread to improve responsiveness. Dealing with lazy symbolication occasionally, you might see symbols in the call tree that are not fully symbolicated, example addresses like 0x1000000000. This means instruments couldn't map the addresses to function names. To fix this, ensure you have debug symbols make sure your build configuration is set to generate debug symbols, usually the debug configuration. Clean and rebuild sometimes, A clean and rebuild of your project is necessary to ensure that the debug symbols are up to date. Verify DSYM files. The DSYM files, debug symbols files, contain the symbol information. Ensure they are present and correspond to the build you are profiling. They are often found in the derived data folder or in the products directory within your project. Symbolicate manually. You can attempt to symbolicate the data manually. This is complex and not usually necessary with a properly configured project. Using logging and custom instruments. While the time profiler is excellent at identifying bottlenecks, sometimes you need more context. Consider using *os_log*. Add logging statements to your code to track the start and end times of specific operations. You can then view these logs in instruments alongside the time profiler data. Custom instruments. For more advanced profiling, you can create custom instruments to track specific metrics relevant to your application. Profiling different build configurations. Debug versus release. Profile both debug and release builds. Debug builds have extra overhead, example assertions, logging, that can skew the results. Release builds are optimized, so they provide a more accurate picture of real-world performance. Ad hoc distribution. Consider profiling an ad hoc distribution build, as this closely mirrors the user's actual experience. The importance of real-world scenarios. Simulate realistic user behavior. Don't just run artificial benchmarks. Profile your app while simulating typical user workflows. Test on a variety of devices. Performance can vary significantly between devices. Test on a range of devices that represent your target audience. 7. Optimizing the code example. Let's apply some optimization techniques to the calculate primes function we created earlier. A common optimization for prime number calculation is to check divisibility only up to the square root of the number and to use a pre-calculated list of primes to filter potential divisors. Replace the original calculate primes call in the button action with calculate primes optimized. Profile your application again using the time profiler and observe the improvement. You should see a significant reduction in the self-time of the isPrime optimized and calculate primes optimized functions. 8. Common mistakes to avoid. Profiling without a specific goal. Start with a clear understanding of what you're trying to measure or optimize. Randomly profiling without a goal can lead to wasted time and effort. Ignoring statistical variation. Performance measurements can vary slightly between runs. Run the profiler multiple times and average the results to get a more accurate picture. Over-optimizing prematurely. Don't spend time optimizing code that isn't a bottleneck. Use the time profiler to identify the areas that will yield the greatest performance gains. Ignoring memory usage. The time profiler focuses on CPU usage, but memory usage can also have a significant impact on performance. Use the allocations instrument to identify memory leaks and excessive memory allocations. Not profiling on real devices. The simulator is a helpful development tool, but it doesn't accurately reflect the performance of real devices. Always profile on the target hardware. Misinterpreting system calls. While system calls can indicate areas where your app interacts with the operating system, I/O, networking, etc., they often aren't a direct cause of slowness within your own code. Investigate further to determine why your app is making those system calls so frequently or taking so long to execute them. 9. Conclusion. The instrument's time profiler is an invaluable tool for identifying and resolving performance bottlenecks in your Apple applications. By understanding how to interpret the data and applying appropriate optimization techniques, you can significantly improve the performance and responsiveness of your apps. Remember to focus on real-world scenarios, profile on target devices, and iterate on your optimizations based on the results you observe in instruments. Practice using the time profiler with different types of applications to develop your skills and intuition. Good luck and happy profiling.